mathematics, we placed a point on the curve at pi divided by 3, drew the tangent, found the slope. It is in fact the same as the slope of our secant, verifying our mean value there. Okay, let's go on. Okay, an object is removed from the furnace and placed in an environment with a constant temperature of 90 degrees Fahrenheit. Its core temperature is 1500 degrees Fahrenheit. When is it 1500 degrees Fahrenheit? Once removed from the furnace. Got to keep that in mind. Okay. 5 hours later, the core temperature is 390 degrees. When was it 1500 degrees? Yeah, at the beginning of, when you first brought it out. So the input is number of hours outside of the furnace, and 1500 degrees Fahrenheit is the core temperature. Okay, and then we have 5 hours later, number of hours after you take it out, its core temperature is 390 degrees. Okay. Explain why there must exist a time in the interval. Which interval? In which interval? 0 to 5. Okay. So the input between 0 hours and 5 hours. When the temperature is decreasing at a rate of 222 degrees Fahrenheit per hour. Is this saying find the time when the core temperature is 222 degrees? No. It's saying between each hour the temperature is dropping that many degrees. Okay, so find the time between 0 and 5 hours when the temperature of the core temperature of this object dropped that many degrees between 2 hours. So the core temperature isn't going to be 222 degrees. Okay, so we don't know what the function is doing. We're not given the function. We have a function, we'll just call it f of t for time. So the function of core temperature with respect to WRT, with respect to time being our input. Okay, so if we want to do this, we want to know that is there a time in the interval when the temperature is decreasing that fast? Now, we can find that if we know what other bit of information. Given, could you plot those points if you wanted to? What else could you do with those points then? If you have those 2 points plotted, you could draw a line between them. If you have a line, you could then determine slope. Okay, I've got some function, I've got 2 points on it. I can draw a line, I can find a slope, meaning that I can find the average rate of change. So, first thing we're going to do is determine average rate of change. So we're going to take f of 1500, whoops, that's not right, f of what? How much? 0. I could take f of, well, okay, you want to start with 3? We can start with 3. It doesn't make any difference, does it? But we can take actually f of 5 minus f of 0 divided by 5 minus 0. Find the average rate of change. So let's see, f of 5 is 390. F of 0 is 1500 divided by 5. So we just have to get out our computation caps or our inspires. What's 390 minus 1500? Divided by 5. And how much is that? Negative 222 degrees Fahrenheit. Okay, this is average rate of change, so this is per what? Degrees per hour. Okay, so if we know what the average rate of change is, we want to know what? Again, Jenna? Instantaneous rate of change. Now, we don't know what the derivative is, do we? So how can we take the instantaneous rate of change what do you think? Well, let's go back to our premise. Imagine that we have a function defined for this. What do we need? For mean value theorem, the function has to be continuous. Okay. Do you think that the implied function is continuous on this interval? What if it were not continuous? What would that mean? What's the output of the implied function? Temperature. Okay, what's the input? Time. If it's not continuous, we're saying that the time exists within 0 to 5 hours where the temperature is undefined. Could that be true? Or that it's going to infinity in either direction? No. Okay, so is the implied function continuous? Yes. Okay. Okay. Third thing we need to do is the implied function, what's the other piece? Differentiable on that interval. Well, let's see. It's continuous. If it's continuous, what's the only type of graph that we have where the derivative would be undefined? Okay, so a very sharp point, meaning that it comes down and back up real quick. Okay, is that possible that the function is going to do? The temperature? No. So is the answer? So yes, if it's continuous, the only way we could do it would be if it did something like that, and that's not going to happen with this. So okay. So it's continuous and it's differentiable, and we have negative 200. It's dropping this fast, so we want to know, could there be a time in there where the derivative could equal this? And the answer, it's not asking to find it. There's no way we can find it. It just says, is it possible? And so the secant slope exists, okay, and is continuous and differentiable, so therefore it is possible, by the mean value theorem, it is possible that a value of time, let's say, exists where the instantaneous rate of change has the same value as the average rate of change, meaning negative 222 degrees Fahrenheit per hour. Okay, that's all we can say. We don't have any other data to go on, but it's continuous, it's differentiable. The slope of the secant does exist, and so by that, then we are guaranteed that there is a time in there. Okay, let's go back and look at that theorem here. It says, if it's continuous and differentiable, then there does exist a value such that this happens. Okay, so that's all we can say. We can't say anything else about it. We can't find it because we don't have enough information. Okay, vertical motion. Vertical motion. This is our, if you want to make a note, this is the same thing as our position function. We've talked about that other times. Height of an object, t seconds after it's dropped. Okay, so it's the height, initial height was 500 feet, and its position can be found with this. Find the average rate of change of an object during the first 3 seconds. Average rate of change during the first 3 seconds. What do we have to do to find the average rate of change? What do you need? Yeah, this is the same, velocity is a rate of change. So this is the, what am I trying to say here? This whole thing here is asking for the slope of the secant. Okay, average velocity. Velocity is the derivative of position function. And so if we're looking at average rate of change of a position of an object as it's moving, we are talking about velocity. Okay, so we need to find S. Well, first of all, what's our closed interval? From 0 to 3, yeah. Okay. We better go through our checklist because, sometimes they trip us up on these. Is it continuous? On the open interval? Yeah, it's just a polynomial. Is it differentiable? Actually, it's we say it is on the closed interval and differentiable on the open interval. And because it's polynomial, we say yes to both of those. Okay, so we have that. So we do know then that there is going to be, we can apply the mean value theorem. Okay. So now let's find that average rate of change. So we'll just say average rate of change, otherwise known as the average velocity in this problem. So we have S of 3 minus S of 0 divided by 3 minus 0. I'll let you work on that just a little bit. When you come up with a numerator value, let me know what you have. Okay. Now this is a case where if you take your inspires and we define the function f1 of x, or whatever number